I think I'm gonna kind of. I think I'm kind of almost gonna have to start from scratch because I got too distracted with the IBM Quantum Challenge and I didn't finish this. I kind of realized I didn't finish this. I did another video on Q control and I wanna make sure that I finish these. So this is about quantum approximate optimization algorithm, and I remember that I kind of read almost everything, and so I'm kind of thinking about how to approach this now, whether I just go to the very top again and I start from scratch, or whether I just go and start from somewhere. Traumatization, revisited, in relation to AQC, why should it work? So why is HV important? Okay, so let's maybe do this. I don't know if I did why should it work, but let's take a look at these. I hope you can read well. But then my face bothers. Okay, here. So, principle, if you can get infinite number of steps and choose angles which exactly mimic the adiabatic path, you'll get the right results. It reminds me of the universal approximation theorem for neural networks. UAT says that if you have a one-layer neural network which is big enough, it can approximate any function, so basically solve any problem. The problem is with the big enough part. The requirements are astronomical for relatively simple problems. That's why we usually don't use gargantuan one-layer networks, but rather just stack smaller layers on top of each other. With QAOA, the case is similar. In principle, we could just keep increasing the number of steps and stay close to the parameters for the adiabatic path. In practice, we choose not to. Smaller, okay. There are some intuitions why it should work, but to be honest, we don't know if it will work, at least without infinite resources. It's an important open question. Some of the researchers, are optimistic because, as it was with neural networks, they have very limited practical applications, and some improvements made them an extremely useful and widely used tool. It's not a problem. Okay, actually, there's a quote illustrating it from a recent paper by 2 of the 3 authors of the original. No one knows if a quantum computer running a quantum algorithm will be able to outperform a classical computer on a combinatorial search problem. Why is B important? HC is easy. It corresponds to the problem that we want to solve, and hence we know why it looks the way it looks. But what about HB? Why do we choose it to be just these and not something else? Why do we even need it all? First, it doesn't need to be just these. We want it to be something that does not commute with HC. Oh yeah, that's a part that I think I also don't really understand. And this choice of HB meets this requirement and is super easy to implement. After the experimentation, we get the layer of Rx gates. The discussion might help you to understand why commutation operation is significant. Okay, let's see. Let's take a look at this. What is the physical meaning of commutation of two operators? I understand the mathematics of commutation relation and the commutation, but what does it physically mean for an observable to commute with another observable in quantum mechanics? Mathematical statement that let us first restate the mathematical statement that two operators A and B commute with each other. It means that A times B minus B times A equals 0, which you can rearrange to be these. Yeah, if you recall that react on a quantum mechanical state gives you a new state in return, then it means that A and B commuting. This is not a trivial statement. Many operations, such as rotations around different axes, do not commute, and hence their end result depends on how you have ordered the operation. So what the important recall that when you perform a quantum mechanical measurement, you will always measure an eigenvalue of your operator, and after the measurement, your state is left in the corresponding eigenstate. You will always measure an eigenvalue of your operator. Okay, yeah. And after the measurement, your state is left in the corresponding eigenstate. Yeah, correct. Okay, so with an X, with a Z measurement, you're getting like +1 or -1, I think, right? Yeah. So those are the eigenvalues. The eigenstates are precisely those states which are known. If you're in state N with eigen. Okay, let me go back. I don't know. Let's just go back here. I'll go back to that later. Another way to look at this is the choice of HB changes the expressibility of our ansatz. It allows us to reach states that we would otherwise never reach. Remember the robot arm from the VQE post. Yeah. Second, why do we need it at all? One part of this is that it is just a part of the setup that came from AQC, and the way that we apply it comes from tutorization. Unfortunately, it doesn't give us a lot of intuition or reason why not to drop it altogether. For me, it's easy to understand this problem if we look at it from perspective of not having HB at all. So what happened in such case? We would just be repetitively applying UC, but once we got into a state which is the eigenset of HC, we wouldn't get any farther. This is basic linear algebra. If we apply an operator to its eigenvector, it can change the length but not the direction. The same applies for So we do this to kind of escape. So this is a step which allows us to escape from the local minimum. That's what it's gonna, yeah. How do we make sure we escape it? That's where the classical attention loops comes in. So we try to find the right. Okay, yeah. I came up with a metaphor which might be helpful to get some more intuition. Imagine you are in a forest full of traps and you want to find a treasure. HC allows you to feel the treasure and move towards it, while HB provides you with a set of rules on how to move to avoid the traps. Without HC, you have no idea which direction to go, and without HB, you cannot make any moves. This metaphor definitely has some limitations, but it should work for starters. That's actually a pretty good one. I mean, QAOA revisited. Okay, sustain, where is okay. The time evolution. I don't know if I shouldn't reread that again altogether. But it kind of makes, yeah, I can, okay. I think I'm getting it. I think I understand. Okay, but let's just go. What does the circuit looks like? So let's take a peek at how it looks like in practice. A simple problem that we're going to solve is the max cut on a triangular graph. The edges have weight 10 and one weight has weight 1, 10, 10, 1. The correct solution for this problem is the cat which divides this graph into two groups, 0 and 1, 2. We can encode the solution into a binary string where 0 and 1 indicates in which group a given node is. For example, 0, 0, 1, nodes 1 and 2 are in group 0, nodes 0 is in group 1. Yeah, okay, as you can see, we use representations where the rightmost grid is the least significant. The cost function for max cut is the sum of costs of all the individual edges. Each individual cost is equal to what? Where zi equals 1 if the eth node is in group 0 and zj equals -1 if it's in group 1. I know such a presumption might not make a lot of sense at first glance, but once you start solving this problem, you will see it's reasonable. Now we can translate this into Hamiltonian form. Okay, so why? The cost function for max cut is the sum of all costs for all individual edges. Each individual cost for each individual edge. Yeah, because that's the cost function. You want to maximize that. So that's okay. So that's the cost See if that works well. I have to turn on this thing here. So these, it's a bit weird. So these is for between edge I and J, and it's a half of, okay, so this is 1 if it's in group 0, and J if it's in -1 if it's in group 1. But what it would, which one? If the ETH node? Okay, I get it. Okay, so the thing is, if they are in different groups, this is going to be minus, right? Exactly. And so then we're going to actually count this. If they are in the same group, then this will actually cancel out, and so the whole thing is ignored. So this means we're kind of ignoring the cost of the elements that are in the same group, and we're only counting the ones which are okay. Why it's a half of W? It's the half of it, probably because you will do this, cost ij is probably the same, right, as cost ji in this case. So you're going to count it twice, so that's why you do that. You kind of make it the half. Okay. So translate into a Hamiltonian. Give me a second, guys. I gotta pause for a second. How can I pause? Okay. Where were we? Yeah. So. Okay. So wait a second. Hamiltonian. Blah 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 blah. So we can now take care. So HC is the cost function. Okay. So these are the qubits: 0, 1, qubit 0, 2, qubit 1, 2. Okay, but that doesn't make sense. These halves, why these halves? Why are these halves in here? This makes sense. It's not, that's not, that doesn't make, that's not what I meant then. So we can take care of HB. This is easy. It's just these. Okay, we'll just go back to these, whatever. Now we need to, I guess the idea is these part of the circuit can be whatever you want, as long as it's not something that commutes with this part of the algorithm. I guess that's the point. Perfect. So if now we need to build UC and UB from this, we can create a circuit out of that. How? Well, this kind of is beyond the scope of this. But this curious. Okay, yeah, sure. I mean, actually, no, I'm not sure. How do you? U1 minus 10. 5. What are these numbers? As I have also not done this manually. I just used some code from a Kiski tutorial. For those of you who are curious, you can find it in this paper. And so there's an actual way to then turn this into a code. Okay, yeah. I guess the point here is, so those things connect the edges, right? So you're doing control, and then you're doing a, what was the U1 gate actually? U1 gate, was it just a Z rotation? No. Yeah, what's the Z rotation, right? Why is software gate time is 0. What is the U gate? 9 p.m. Is it just a phase rotation? U1 gate. Yeah. No, phase shift gate in Qiskit. F U1. The X and U1 gate from Debian Qiskit. I didn't want to. The U1. Yeah, that's the phase gate, right? Yeah, exactly. That allows you to do this. Okay. So if let's do this quick. Okay, let's do this. I feel I'm slow today. So the point here is if you're because here you have a here you have a super here you have a super. Why is it not painting? Exactly. So here I've got a superposition. So it's kind of applying for all values, right? But let's say we have the, I don't know, 0, 1, 1, right? And so what this would do, or you have like 0, 1, 1. So this would be 1, 1, 0, and not these. So, okay, so here, so rotating the phase, but then this only applies in the case where kind of each of those elements is kind of 1, 1, right? So in this case, this is not applied at all. Well, it's applied here. But again, it's maybe uncomputed later on. Because then it's like, so only in this case, but then it's 1, 0, right? Because they're from the same group. Okay. Yeah, so only if they are from different groups is when it's counted. So this means if it's 0, 1, right? This doesn't have effect, but it's going to get kind of counted. So just for the element where it's 1. Yeah, so that adds the 5. Okay, I get it. So look at this. So if it's 0, 1, 1, right? In this case, because these two qubits are from a different group, you're gonna have a phase rotation of 5, whatever that 5 is, okay? But I guess it's the half of 10. Because those are also belonging to different ones, you're also gonna have that. So you're gonna have another phase of 5. So you accumulated 10 now. Those two guys, because they belong to the same group, this is going to turn that into 0. But now you're going to have these here, which you usually, I'd say, you wouldn't want to have. So this, I'm not sure I understand why it's here. But it's somehow these things kind of it is encoded in that. Apparently there's an algorithm here to do that in section 4. Can I switch this? Yeah, baby. Oh, yeah, here you go. Boom. No! The page went away. Section 4. Using quantum computers. Section 4. Section 4. Oh, I missed it. Primitives. That's okay. As mentioned, the idea of using a quantum computer for obtaining molecular energies for what is this? The present section contains what is kind of the chart of okay, that's the chart of the composition. The chart of the composition using a second quantized percent for the composition of the exponential map of each term of the Hamiltonian. However, the terms of the composition do not always commute. The goal of the chart is to approximate the time evolution operator. So if this is the sum of local Hamiltonians, is a chart number. Quantum circuit primitives. Each term of equation can be exponentiated using the universal. So those are control knots. They're not control. Wait a second. I'm confused. I'm now confused. Those are control Zs. Those are controlled. Those are U1. Okay, those are controlled Zs. Sorry. So if we stick to our number 0 here, so 110. So those are control. So they're gonna minus 10, minus 10, minus 1. So just first consider the exponential map of to create the unitary gate. The C0 gate can be used to first entangle 2 qubits, then RZ gate is applied and followed by a C0 gate. Okay, we'll get into these, I guess, at some point. How this is constructed, but okay. So the phases. So the idea is you're doing control. Those are control Zs at the end of the day. No. I don't know. Here you're doing something different. Here's a bit of a, okay, so it's control Zs. I don't understand what are those doing here in the middle. Wait a second. I guess, okay, so this is minus 10 and then those guys, okay, so I know. So what this is doing is the following. So this is saying you, okay, so I'm going to do a control Z on minus 10, right? So this means for the case this is 1, 1, right? Otherwise, because if it's 0, 1, it's in 2 different groups, and that's when we want to count it, right? And so it's only going to count half. So the half, that's what we want. We want the half of 10, which is 5. So it kind of, it's in both places, because if it's 0, 1 or 1, 1, okay, so this is just a correct pre-correction. So if it's 0, 1 or 1, 0, right? Maybe it's like this. So you want that 5 to be added into your cost. Now, the problem is that these 2 gates would also be triggered if you have like a 1, 1. So in this case, this 1, 1 is corrected by applying a phase first of minus 10. So if that's the case, then these 2 other phases kind of bring it back to 0. Okay. And then you do that for this qubit, for this qubit, for this, for each of the edges of the graph. Ah, okay, I get it. Yeah. So basically, you just really, I think the reason you do need those rotations is because, I mean, here you're calculating the cost in the phases. And so that HB kind of is there to turn those into something measurable, right? Because in your block sphere, if you're like, that's a beautiful block sphere. If you're rotated across the around the z-axis like that, and instead of you're here, right? A next rotation will take you somewhere. I think so. I don't know. That's the feeling that I have so far. Okay, but we understand the circuit. The circuit's okay. So we're not gonna each of one thing. You can see the first are parameterized with 10 times. Okay, so this is actually, there's actually a variational part in there. 10. This is just a layer of Rx parameterized two times better. Okay. So what is appropriate? Why is it appropriate for NISC? The data is scalable. The more steps we want to have, the more power QA has. With most current devices, we're limited to 1-2 steps. Similarly, VQE is somewhat resistant to noise, which is also shown in the same paper from Google. Is somewhat resistant to noise. Even though I've described only one particular way of creating nonsense, there's actually some flexibility, and therefore you might be able to tune it towards specific architecture. Relation to VQE. VQE and QA are often mentioned together. VQE is often described as an algorithm good for chemistry calculations, and QA good for computer. It's worth to understand the relation between the two. The QAOA can be viewed as a special case of VQE. In the end, the whole circle we've described above is just an ansatz, parameterizable by the angles. And since the Hamiltonian contains only z terms, we do not need to change the basis for measurements. Okay, then it's clear. There are, however, a couple of things that make QA different. The form of the answer is limited to alternating the form we've seen. We're restricted in terms of which times the Hamiltonians we can use, Ising Hamiltonians. This also means that we don't need to do additional rotations before measurements as we did in VQE. At least I think the most fundamental difference is the goal of the algorithm. In VQE, we want to find the ground state energy, and in order to do that, we need to reproduce the ground state. In QAOA, our goal is to find a solution to a problem. To do that, we don't need to find a ground state. We just need to find a state which has a high enough probability of finding the right solution. Okay. But let's back up a little bit so we understand the circuit, the way the cost is built. So what QA is saying is build your cost function all in one kind of, in one of the axes, right? In theory, you could do whatever you want. Like in theory, you could also do this part, like this could also all be like control nodes, and those actually like Rx, like, right? And so it's all on the X basis, and then this could then be like Z rotations, right? Could also be done this way, I think. The main restriction is those things should not commute. And the reason being that you're trying to simulate this tritorization. That's what you're trying to simulate. let's go back to these a little bit, because I found this pretty interesting. So okay, let's do a bit of the background again. So in this section, I'd like to review two ideas which come directly from basic quantum mechanics: time evolution of quantum system and tritorization. There's an operation which is quite common in quantum computing, taking operator A and creating another form UA, which is this. But why do we do that? Well, it comes from the Schrodinger's equation. What it says is that the change in time of the state of a quantum system described by a time-independent Hamiltonian H depends solely on the form of its Hamiltonian. Let's reread that. So, change in time of a state of a quantum system described by a time-independent Hamiltonian is only the form of its Hamiltonian. And if we solve the equation, we see that the dependency is this. Okay, so that this is the way the time-independent thing change affects, or the state evolves. This tells us that if we take some state, phi 0, and act on it, evolve it with a Hamiltonian H, for a period of time t, we'll get a state like this, okay? So that's just quantum mechanics. If this sounds abstract, imagine an electron orbiting the proton, hydrogen, system is defined solely by an interaction between these two particles. So some different equation, we're able to get a formula describing the state of the system after time t. And if we do the math, it will look like this. The key point to remember, whenever we see an operator like it looks like this, you can understand it as an evolution of the quantum system described by Hamiltonian H. Until this point, we've made one silent assumptions. Since Hamiltonian we have solved was time independent. But when we take a look at a Hamiltonian we use for accuracy and change alpha to t, we cannot pretend it's time independent, depending on how complicated this time dependency is. This might complicate the solution we've presented a little bit or a lot. In later cases, it might be possible to solve to make some approximations. It's going to do the same with time evolution of a quantum system for an operator UT. UT is actually a shorthand for UT-T0, which means that we act for time t starting from t0. We can write these as, yeah, okay, so you're kind of approximating to the bigger, the better approximation we can get. Keep in mind that the time difference. Okay, so I think what this whole thing is saying, really, what kind of function? A plus we are applying alternatively A and B for time intervals. Say it again. If we're not familiar with this, the Suzuki-Trotter expansion or tritorization. So expansions using mathematics like Taylor series expansion. If we're not familiar with this concept, if our Hamiltonian has the following form, e to the a plus b, we can use the following relation. We can look at this as approximating time evolution by a plus b by applying alternatively a and b for time intervals of 1 divided by n. Okay. So QAOA creates the state where UHB beta is this guy here. So we've got these in here and we've got these in here. HB and HC for time. So this is the Hamiltonians. So we're evolving the system like that. Okay, but so like combining the two previous points, we can see again somewhat mimics the adiabatic evolution from the ground state of HB to the ground state of HC, which encodes our solution. Remember Ising model. So answering the question in the previous paragraph could be given right choice of as the approximation of a QC. Analog to Q. First of all, the goal is different. QC goes to get a ground state. Goes to not really get the exact ground states to get state which has good enough overlap with the ground state. Make the evolution using a QC, but we don't do that in QAOA. We can choose angles arbitrarily using some classical optimization strategy. Give me a second, guys. I gotta pause for a minute. Sorry, back there. So, back in here, why should it work? In principle, you can get an infinite number of steps and choose angles. Approximation. But what are we approximating? How is HC encoding? So, how is the cost encoding the? How's HC encoding the solution? How is HC encoding the solution unless what you're doing is you're rotating the phases of those elements in your superposition. So you're actually computing the cost. And so when you do these, it's an X rotation. It's a rotation around the X axis. So I see if you open Quirk, I mean, that's really, so let's say we go here, right? I mean, the rotation around the x-axis in this case doesn't have any effect. If we had a quarter of a turn, or say a t-turn, right? And you do, I don't know, say a next rotation, like say this, right? I mean, you see the difference, right? So this actually does have an influence. What was I doing? What did I say? T. Right. So you see here in the block sphere that this now has got a probability of measuring 0 or 1 that's different than 50-50. So that's the whole idea. That's the whole idea, is that this cost Hamiltonian is basically taking you so is from your it's the elements. So the elements that you're going to be phasing are the ones that you will then, let me see if you will then kind of be able to, so if I do this, let's put it this way. Let's imagine I phase I'm just phasing this element 1, 1, 1, right? And now I apply a bunch of rotations like these. So this element is now more probable. This as well, right? But this element is more probable to be measured as well. Okay. Whereas if I change these, the 101. Okay, so the two elements. So you see what's happening here, right? So is this working or yeah? So this is flag the element 101 with like 180 degrees phase. And so this basically means that those elements, after applying the mixing, right, it's okay. They get increased probabilities. Okay, and this actually can be anything that doesn't commute, really. So I could also do it the other way around. Let's say that I do. Let's say that I do a control, like let's say this is these, right? And let's turn these guys into T gates. No, that doesn't work. Why that doesn't work? Because then I cannot, I cannot start in superposition, right? If I do it this way. Yeah. Yeah, it's bad. So I should be, well, I can be in superposition, but then I probably got to apply here. No, the superposition. No. Sorry, another set of Harman gates. No, why? Wait a second. So I would go. Control Z. What if I do these? Then apply a T gate. No, that doesn't work as expected. Do you have to use, that's my question, do you have to use this to kind of build these on the Z dimension? Or cannot you just build it in the X dimension and then apply? Because I guess this is related to these, right? Because you're man, it's late. I think I'm getting tired. But I'll probably try to do that in the next video. There's got to be a way that you can play with different dimensions as long as they don't commute. That's the idea. But I think I'm getting it. So I think that was not my idea was not far off. It's the whole. But I like the article. So I like the post. I like the introduction, tutorization concept here. This is just okay. So it's just one way to do it. Was that the one thing that was not really clear? Was the why is it supposed to be the ground state that we're looking for? Which we're not, are we? Anyway, it works. And it works because that's what we're doing. So we're basically implementing a cost function in here, and then we're putting this so-called mixer or this HB in here, which basically it rotates everything. And so the stuff that we have faced in here will now affect the probabilities that those elements get measured. In the case in the case of this particular example, it's kind of fine that two things get flagged, like the actual opposite things get flagged. Because if you remember here, it's gonna be faster with my mouse. So if we flag 1 1, say 1 1 1, right, and then we apply, I don't know, this mixer, right? So you can see that the actual opposites are enhanced, so they have higher probabilities. But that's fine, because actually at the end of the day, if what you're doing is you're coloring a graph, I mean, it's the same saying that they're all from the group 0 than to say that they are from the group 1. If you're flying this element 1 0 1, it's the same to say that that the element in the middle is from a different group, because both representations are correct. So you're kind of doing twice the work, but it's not really needed. So there are always two possible solutions, right? It doesn't matter which color you pick, so that's why it works. Yeah, so that's the idea. So you're doing some. I mean, it's funny because that's the same principle you have, or it's a similar principle you have with Grover's algorithm, isn't it? I think you can approximate Grover's algorithm with these. Yeah. Actually, I think I have seen that before. You can approximate it because that's the same principle. As you play with your phases, and then you do this kind of rotation, so the stuff you've changed in here is now going to be affecting the amplitudes. Yeah. Okay, cool. But I think that's it. There was one part that was a bit confusing for me, which was the whole thing with HB and being and ground stuff, ground state. What was that? That was the housing models. Oh, this adiabatic part in here. So I'm gonna say this was a bit confusing. Then the processing will always stay in the ground state, which means that the n will be the ground state of the cos Hamiltonian. Of course, it's not an easy thing to do when certain conditions apply, but in principle, if the evolution is slow enough, we're able to find a solution to any problem. If we can encode its solution in the ground state of HC, we use the word evolution for the process of changing the quantum system. Also, we often use ground state, also another Hamiltonian ground states. We can now construct a new Hamiltonian of the form. This is described. Okay. Yeah, whatever. It works because that's what it does. And so, and I mean, and then you just, so the variational part with the lambdas is just to add that kind of learning process to it, right? That you kind of change. You can optimize those, so you optimize those parameters so that this combination of steps gives you the so you're kind of maximizing or minimizing. I think that's what you want to do, right? Minimizing the cost or maximizing the cost, whatever. Probably minimize, whatever. You minimize or maximize, and that's classical optimization. But that's why it works. And the difference between this and VQE is the VQE is, so that's a special case of it. VQ is a more generic. That's actually an ansatz. Yeah. VQ is a sort of, but they're the same. They're just really the same. VQ is more general in the sense that you can construct more complex. If your Hamiltonian is made of different observables, or I don't know if I'm using the right. Yeah, then you kind of got to decompose this and run 3 different or 2 different circuits, and then kind of at the end add up the results. And here's like, hey, no, just focus on one dimension. That's the z dimension. Do your cost function there. then mix it up, right? So add this mixer in here and repeat the whole thing again. And so from here you can get to Grover as well. Yeah, I think so. I think what I might do is probably go through. I've seen here there's some tutorials, and I see there's one by Guillaume Verdon, and I probably want to do these because I think that can be an interesting one to go through, and it's in Circ as well. So we can see how this is built in Circ. Cool. So I'll do that next time, and that's probably going to be the closing one for the QAOA revisit, because now I've got a good refresher, and I think I know what this all means. So and why this works. Maybe, I don't know. Maybe we can try to solve another problem with that. Maybe it's going to be more educational to actually take that notebook as a reference from the MaxCat problem and try to do something else with it. Maybe that's going to be more educational. So we could do a mixture of both. I can take these, but I can try to solve another problem that's not the MaxCat, for example. But at the end of the day, that doesn't really change anything. It just changes the cost function. So I don't know. We'll see. But it's more intuitive if you understand what is it doing. So it's kind of adding step by step. It's phasing step by step based on whether those element or those two qubits belong to or have a different value and belong to different groups. Yeah. Anyway, good. Good night, people. Thanks for watching. It's fun. It's been fun. It's been fun.